So we are on chapter 13. We're done with 13.1, 13.2, and this is 13.3. So we are on page 1. Page 1. Very well. In Calc 1, Calc 2, you learned about the length of a curve in two-dimensional space. So this is recall. For a function like y equals to f of x, the graph of this function is just a curve in two-dimensional space. This is the graph. And suppose you want to find the length of the curve here to here. What is this length? So we need x between a and b. And if you divide this little curve into small pieces, you have some line segments, very small. By using the Riemann sum, you can find the length of this curve. So officially, we have the integral a to b square root of 1 plus the derivative of the function squared dx. Of course, if it's hard to take the derivative with respect to x, and if you get a complicated integral, you can always switch to y, c to d, integral 1 plus, so suppose you rewrite this as function of y, and you take the derivative and raise it to 2 with respect to variable y. So x is g of y. We can generalize the idea to any curve in three-dimensional space. Very well. So our function is defined this way. Let function is defined as x equals to f of t and y equals to g of t. Then the length of curve in three-dimensional space can be calculated using integral. Suppose your t ranges between a to b. This is square root of, you take the derivative with respect to t, you take the derivative with respect to t, you raise each of them to the second power and add them all together. So f prime of t squared plus g prime of t squared dt. Okay, it is in two-dimensional space. Now we generalize this to three-dimensional space. Now, in three-dimensional space, of course, we have x, y, and z. So let x be f of t, y be g of t, and z be h of t. And suppose your t ranges between a to b. The length of the curve is equal to the integral a to b square root of the derivative of x with respect to t squared plus the derivative of y with respect to t raised to the second power plus the derivative of z with respect to t squared. Of course, we take the integral with respect to variable t. And we can generalize the idea to four-dimensional space, five-dimensional space, and so on. So in the n-dimensional space, the length of the curve is equal to the integral a to b square root of, we take the derivative of x with respect to t raised to 2, the derivative of y with respect to t squared plus the rest of the coordinates d. There you go. Let's go over one example to see what's going on. We're on page 2. Page 2. Example. So in this case, you have, okay, a circular helix with a vector equation. So we have helix with equation. What is the equation? It's cosine t, sine t, and it's just t. Very well. So this is your function, and t, we don't have t, and let's see, it starts from the first point, initial point, which is given as 1, 0, 0, and the terminal point is 1, 0, 2, 5, 1, 0, 2, 5, and the question says, find the length of this helix. Okay, very well. So what do we have here? We have our x, we have our y, and we have our z. This is x of t, or your function f. This is y of t. The second one is y or g of t, and z is given as h of t. So you have all of the information that we need. You just need to follow the formula. The length is equal to the integral, lower bound, upper bound, we're going to talk about that, square root of the first coordinate raised to the second power with respect to derivative, so the derivative of cosine t squared plus the derivative of sine t squared plus the derivative of t squared dt. Okay, perfect. So L is equal to the integral square root of the derivative of cosine minus sine squared plus the derivative of sine, which is cosine squared, plus dt. Now sine squared plus cosine squared is equal to 1. L is the integral of square root of 1 plus 1 dt, which is the integral of square root of 2 dt. Very well. So you have 2 points. What do you have? You have your x, you have your y, and you have your z. Z and t are the same. So t is equal to 0. Remember that. You can set these equal to each other and can actually calculate your t. Let us find the second t as well. So your x, your y, and your z are given. So t is equal to 2 pi. T ranges between 0 and 2. There you go. This integral is super easy. You have square root of 2, and t ranges between 0 to 2 pi. The final answer is equal to 2 square root of 2 times pi. This is the length of our curve. Okay, let's continue. So note that any vector function can be represented by more than one parameterization. What do I mean by that? Take a look at this. Let R of t be given as t squared and t cubed. T ranges between 1 and 2. 1 and 2. So here's a question. Can you use a different parameter? Can you use a different variable? Remember that when you talk about parameterization, you're using a parameter or a variable. It's a variable. Here, I use variable t. We can use any other variable that you want. What do I mean by that? I say, hey, I want to rewrite this vector function this way. This is my choice. You might have a different choice, another option. I'm going to rewrite this function using a different parameterization. How do I do that? Okay, I'm going to start by changing t to a function, any function that you like. Suppose I want to use an exponential function. Let us use an exponential function. So suppose I take t to be e raised to u. This is absolutely my choice. You can take t to be sine of u. You can take t to be cosine of u. Anything that you like. So when t is equal to e to u, t squared is equal to eu raised to the second power, and t cubed is eu to the third. So what's the change in t? T ranges between 1 and 2. Since t is between 1 and 2, e to u, you're replacing this one, e to u is between ln of 1. So t is equal to 1, e to u is equal to 1, so u is ln of t. If you want to rewrite this to solve this, your u is equal to ln of t. So ln of 1 is equal to 0, and it is ln of 2. So e to u as a new parameterization is between 0 and ln of 2. So if you switch from t to u, you have to use a new boundary. The lower limit is 0, and the upper limit is ln of 2. So let's go over one example, see what's going on. So we are on page 3. Example. So suppose you have your helix RT, which is cosine t, sine t, and t. And what's given, you know that you want to re-parameterize the helix with respect to the arc, with respect to the arc length. So suppose you have an arc length which measured from one, 0, 0 in the direction of increasing. Increasing t. There you go. So we want to reparameterize the helix with respect to arc length. So we just learned how to find the length of an arc. What else is given? Measured from the initial point. Initial point is also given. We don't have the terminal point. So let us follow the definition of the arc length. Let us call it S instead of L because we want to use a new parameterization. And when you use L, it means that you have a fixed length. L is a constant, L is a number. So instead, you're going to use S as a new parameter, as a new variable. This is equal to square root, the integral of square root of the first component derivative squared. So the derivative of cosine, you already took this, you know it is sine t squared plus the derivative of sine, which is cosine t squared, plus the derivative of t, which is 1 squared dt. The initial point, t is equal to 0. The ending point, the terminal point is not here, so we're going to use a general variable like t. So S, this new variable, new parameter is equal to integral 0 to t square root of 1 plus 1 to dt. Okay, this value is equal to, let's change this variable to like dw to avoid any confusion here. This is equal to square root of 2, and your variable ranges between 0 to t, so you get square root of 2 times t. So this new variable is square root of 2t. It means that your t can be replaced by s over square root of 2. So your function RT is equal to cosine t, sine t, and t now are of S. New parameterization, I'm changing my old variable to a new variable, which is equal to cosine of t is going to be cosine of S divided by square root of 2, comma, sine of t is now sine of S over square root of 2. And t, which is just S over square root of 2. Comma, S over square root of 2. This is your parameterization. So if the question says, reparameterize with respect to arc length, you're going to use the arc length formula, the integral. So let's talk about curvature of a curve. How smooth a curve is. So let's define something first. Definition of a curve being smooth. So in general, we say that a vector function like RT is smooth if we take the derivative of our vector function. The derivative of our vector function is never 0, and so the rate of change of your vector function is never 0, and it is continuous on the given interval. So suppose you have a curve. This is curve C. If you have a tangent vector, remember that the tangent vector to the curve is R prime. We talked about this in last lecture. If you take this arrow and start moving along your curve, there is no gap, there is no move, and it continues smoothly along your curve. So since it's tangent, it is going to be like this. The rate of change is never 0, and it is continuous. And curvature is defined this way. Curvature of so we're talking about a function, a vector function of like R, a vector function R, it's defined this way. K of t, which is equal to. So when you're talking about the curvature, you're actually talking about the magnitude. So it's actually defined as the derivative of a unit tangent vector. You take the magnitude and you divide it by the magnitude of your tangent vector. A curvature can be negative, it can be positive, and it can also be 0. For example, if you think about the straight line, the curvature of a straight line is equal to 0. And remember t is the unit tangent. Let us go over one example together, see what's going on. So, example. Question says, find the curvature of the following function. So, our function is RT equals to A cosine T and A sine T. So take a look at this function. What does it represent? So this is your x and this is your y. Think about it this way. If I take x, if I take y, x squared plus y squared, what do we have? X squared plus y squared is equal to, we get a squared cosine squared plus a squared sine squared, which is a squared cosine squared plus sine squared is just equals to a squared. So we have equation of a circle centered at the origin with radius a minus a minus a. So our goal is to find the curvature of this circle. So let me erase this one. I'm write down the answer for you. So the curvature formula is just down here. So what do we need? We need to take the derivative of the function. We need to form the tangent, unit tangent vector, take the derivative of it, and see what's going on. So to find the curvature, first, write this function down. RT is A cosine T, A sine T, and your R prime, the derivative, is equal to negative A sine T, A cosine T. So on the denominator, you need the magnitude. The magnitude is equal to square root of A squared sine squared plus cosine squared, which is equal to just A itself. On the numerator, first we have to find the unit tangent vector, take the derivative, and then find the magnitude. Now, let us find unit tangent vector. So your unit tangent vector is equal to R prime divided by the magnitude of R prime. R prime is negative A sine T, A cosine T, divided by the magnitude, which is equal to A. So unit tangent vector is negative sine T and cosine T. I'm just dividing each of the components by A. Now I'm going to take the derivative, which is equal to negative cosine T, negative sine T, and then I'm going to find the magnitude. The magnitude is equal to square root of cosine squared plus sine squared, which we all know is equal to square root of 1 or 1. So on your numerator, you have 1. On the denominator, you have the curvature of your circle is 1 over the radius. Curvature not as a vector, just the curvature, equals to 1 over derivative units. So let's write one here for you on page 4. Or another formula, the curvature of a vector function is equal to the magnitude of. So on your numerator, you can actually find the cross product between the first derivative and the second derivative of your vector function, then find its magnitude, divided by, take the first derivative of your vector function and find the magnitude, then raise it to the third power. This is equal to the magnitude of the rate of change of the unit tangent vector divided by the magnitude of your derivative of the vector function. Let's go over one example together, see what's going on. Example. Question says, find the curvature of, this function. R of t is given as t squared and t cubed. So what do we need? We need the first and second derivative, and then finding the cross product. R prime is 1, 2t, 3t squared, and the second derivative is 0, 2, and 60. Okay. Now we find the cross product between them, which is the determinant I, j, k, 1, 2t, 3t squared, and 0, 2, and 60. This is equal to I, 12t squared minus 6t squared minus j, 6t plus j, 2. Then we find the magnitude. This is equal to 6t squared, comma, negative 60, comma, 2. So the magnitude is equal to square root of 36 t to the 4 plus 36 t squared plus, there we go, here we can factor out 4, or you can just say this is my radical. Yes, let's leave this guy as it is. So this goes on your numerator. On your denominator, whatever you have as the derivative, you take its norm or magnitude and raise it to 3. So the magnitude of the derivative is equal to, let's take a look at this. It's square root of 1 plus 4t squared plus 9t to the 4. So the curvature is equal to, we get the factor of 4 inside the radical, we get 4, 9 t to the 4 plus 9t squared plus 1 divided by square root of. Here you have 9 t to the 4. So let's see, everything is correct. 9t squared plus 4, 9t to the 4, 4t squared plus. Okay, here we can write this guy outside the radical. Is 2. What else we can do? Let's see. And this guy goes to the 3. So remember that this guy is as x times 3. So this is the curvature formula that we have. We cannot actually simplify this more. We can, just get rid of one of the radicals, 9t to the 4 plus 4t squared plus 1. It's multiplied by square root of 9t to the 4 plus 4t squared plus 1. Just leave it as it is. So this is the formula for your curvature. Now, if the question says, what is the curvature at time t equals to, for example, 0, t equals to 1, t equals to 2, t equals to 3, and so on, you can just plug that in and calculate the curvature at time 0, temperature 0, and so on. So the curvature at 0 is equal to, for example, 2 times square root of 1 divided by square root of 1, which is 2. And if t is equal to 1, we get the curvature at 1, which is equals to 2 square root of 9 plus 9 square root of 19 divided by square root of 14, and so on. That's how we calculate the curvature in different time values. Let's see what we have. So another formula for you. If you actually have formula for your function, y depends on x without using any vector function. In this case, the curvature for function y equals to f of x, the curvature is actually calculated as you take the second derivative of your function and you divide it by 1 plus y prime raised to 2, and you raise everything to 3. For example, question says, find the curvature of the following function, y equals to x squared, and the initial point, 0, 0, and terminal point is 1. There you go. So let's follow the formula. What do we need? We need the first derivative, we need the second derivative of this function. Y is x squared. So the first derivative of the function is 2x. The second derivative of the function is just 2. So the curvature at x is equal to 2 divided by 1 plus y prime, or x squared raised to 3 halves. When x is equal to 0, the curvature at 0 is 2 divided by 1, or 2. The curvature at 1 is equal to 2 divided by 1 plus 4, 5 raised to 3 halves. Okay, let us just approximate this. 0.18. We can find the rest of the curvatures. For example, curvature at 2. 2 divided by 1 plus 16, so 17 raised to 3 halves, which is approximately, the square is equal to 0.03, 0.03, and so as you can see, the curvature is decreasing.